the word line too long?
Yeah, also because of the word line, the frequency, clock frequency low, then the word line open too long, so then you also can flip.
Okay.
Yeah, that's a couple. Okay.
So you mentioned the mismatch between the two transistors before. Is the mismatch mainly due to the mismatch in threshold voltage?
Yeah, we will talk about that in maybe next lecture. Or maybe at the end of this lecture, we will go to that point. Okay, so this is a brief summary of what we discussed. So the read operation, we need to consider this 0 to 1 disturbance. We want to prevent this one from happening. And then write operation, we need to consider the 1 to 0 transition, and this one happens first. And we need to make sure we have enough pulse width to make sure this 1 to 0 transition happens. So we talk about the static analysis and dynamic analysis for the read and write operations. And here we compare those two as we discussed. In the read operation, we care about the lowest pulse, and the lowest pulse actually is finite in the reality. So then, if you consider this, the read or hold margin actually is underestimated in the static analysis. And then the write margin is overestimated in the static analysis. So this is what we just discussed. And then if we stay with 6T design, then we have this conflict. And to make the better read, we need larger beta ratio. That means stronger pull down and weak pass gate. And then for the benefits of the write operation, we want smaller gamma ratio. That means weak pull up and stronger pass gate. So we have this conflict. One wants weak pass gate, one wants strong pass gate. So this is because we share the pass gates during the read or write operations. Okay, so this is a quick summary, and we can move on. So if you look at the design considerations, we talk about the noise margin, but there are other design metrics. For example, the speed of the operation, let's say the read speed. And we briefly discussed this before. So any delay is related to the cap you want to charge or discharge, and then multiplied by the voltage change, and then divided by the current. So let's say the delay is determined by the precipitate cap of your bit line or bit line bar, and then multiplied by the delta V, the voltage change on the bit line or bit line bar, and divided by the current through the pass gate. And then this is for the speed, and then another important metric is the leakage current in the SRAM cell. Because this is volatile memory, even you don't use it, then you have to maintain the power supply to keep the data. So we will have the leakage current. And this leakage current is the I-off of those transistors. And back in the lecture 2, when we review the CMOS, we talk about what is the off current, what contributes to the off current of the transistor. So if you look at those 6 transistors in the SRAM cell, you will find out that the total leakage current of one SRAM cell, actually only 3 transistors are leaking. So I will not do it for you, but you can check by yourself. So the leakage current of the 6 transistors, actually only 3 transistors are leaking, and 1 pull down and 1 pull up and 1 pass gate transistor is leaking. So this is the contribution to the leakage current that will translate to the standby power of your SRAM array, or let's say your cache, even you are not using your phone. Your battery is still being drained because of the leakage here. So here we are going to discuss some of the techniques to minimize the leakage, let's say leakage reduction in the SRAM. So the leakage is due to the, let's say, the VDS is non-zero of some of those transistors. And you know, when we talk about the leakage, this is, let's say, for NMOS transistor. The leakage happens even when the gate is zero, but you have a VDS non-zero. For example, if this is VDD and this is zero, so you have this leakage current. This leakage current depends on the VDS. So here, one idea is to minimize the VDS during the standby or the hold mode of the SRAM, which you don't do the read or write operation, then you hold the data, that is the standby mode, and you want to reduce the bias difference between your drain and source of those transistors. So let's look at the conventional design. So this is the conventional design where this is the hold mode. When we turn off the word line is zero, right? So this word line is zero. So those two transistors are off, and this is in the hold mode. And then the beta and beta bar always pre-charge to VDD. So let's assume this VDD is 1.5 volts in this case. So you can say that many transistors will have VDS like 1.5 volts. For example, if you look at this transistor, this storage node stores 0. Let's assume it's 0. Okay, that means the other one is 1, so it's 1.5 here. So this transistor, you look at the VDS, is 1.5 volts, right? So that means you have the current, leakage current here. And similarly, for this transistor, you will see 1.5 volts, because here this is 1.5 volts, this is ground. So you have 1.5 volts across that. So those two transistors are leaking, and also this transistor is leaking, because this gate line is 1.5 volts and this is 0, so you have VDS 1.5 volts. So those transistors are leaking. And in this design, it's proposed to modify the supply voltage during the hold operation. So what you can do here is to boost the VSS to be above 0, let's say 2.5 volts during the hold operation. And if you do that, then you can look at the bias condition. So then this node 0 will not be 0. I mean, the data 0 actually will be 0.5 volts here. And data 1 is still 1.5 volts. If you look at the VDS, like this cell will become 1 volt. Previously, this one is 1.5 volts, right? So you can check the bias difference between those nodes, and you will notice that the bias will be reduced between those drain and source in the right-hand side. So that will greatly suppress the leakage current, because the leakage current exponentially depends on the VDS. So you can modify the supply voltage during the hold operation. For example, here you modify the VSS. So this is one technique.
But are we not reducing the noise margin with this approach?
This you only apply this for hold operation, and hold operation, you know, is not less a concern, because mostly read operation is a concern. So this is one design. The other design is you can somehow engineer your transistors. You can have different threshold voltage for the transistors. You can have a dual threshold voltage cell, and this is possible by device engineering. You can use different doping level for the different transistors, so you can tune the threshold voltage. And if you want to reduce the leakage, of course you want higher threshold voltage. And what you can do is to have higher threshold voltage for those cells here, because the key leakage path will be from the VDD to ground. So if you have higher threshold voltage of those transistors, then it will help the leakage. While you can use low transistor, let's say those transistors are high VT. And then for the pass gate, you still use low VT, because the pass gate, you need current to read out the data, and then you want large on current, so you have to use low VT for the pass gate. So you can engineer this, and if you do that, then you can improve the noise margin as well, and while reducing the power consumption for the standby mode. So there are many techniques to play with for the SRAM circuit design. And the dual supply voltage is very common these days for the advanced SRAM cell.
I'm sorry, this tag is for hold or for right, for the all.
This in this slide is for the hold operation, but even in the write operation these days, people use dual supply voltage as well. So that means your word line voltage may not be the same as your power supply VDD here. You can use different voltages to engineer your SRAM cell to certain, let's say, applications, right? If you want to read faster or write faster, depends on your targets. You can engineer this. There are many design tricks. I will not go through all of them, and this is still active research area. So every year still there's, and maybe not recent 2 or 3 years, but still, let's say 5 years or 10 years, from 10 years ago to 5 years ago, still every year in ISCC conference, there is a SRAM session. And there are like 4 or 5 papers talk about the design techniques to improve the SRAM stability or SRAM power consumption or speed in the advanced scaled technology nodes. There are still many tricks at the circuit level to improve this. Okay, so then we will move on to the next topic, which is the SRAM layout. Okay. So here is a history of the SRAM cell evolution. And in the old days, like 1990s, so like 350 nanometer technology node. And at that time, the SRAM actually is not 60 SRAM. At that time, there are different kinds of SRAM cell. I will show that in a minute. But after the industry switched to, let's say, 250 nanometer or 0.25 micrometer node below, 60 SRAM cell becomes the mainstream, and even today is the mainstream. You read the paper like 80 cell, but that one is not the mainstream technology because the density is still better for the 60. If you have special applications, special requirements, you may use like 70, 80 design, but for the mainstream and product, then 60 is still the one. And so SRAM cell scaling religiously scaled by this 0.5x per generation till today's 7 nanometer technology node. So the Morse law does not stop here, but of course the cycle from one generation to another generation may be extended from 2 years to maybe 4 years these days. But from one generation to another generation, this scaling is still valid. So let's look at the technology evolution for the SRAM. And in the old days, like 1990s or even 1980s, so the SRAM cell are not like today's 60 cell. At that time, there are variants like pure NMOS design. So for example here, for those designs here, those are not PMOS transistor. Those are all NMOS design. So you can have pure NMOS design. And actually there are two kinds of design depending on the transistor. Here is the enhancement mode or depletion mode. So do you know what is enhancement mode or depletion mode of the transistor? So basically for the NMOS, the VTH is larger than 0 or smaller than 0. So let's say the enhancement mode I think is VTH larger than 0. Depletion mode is VTH smaller than 0 for NMOS. Okay, you can change the doping and you can do that because the VTH depends on the doping concentration. So this is the old technology. At that time, PMOS is not that mature, so you use NMOS. Of course, the problem here is that you have the ratio logic. That means you cannot achieve, let's say here, pure 0. Because you have two NMOS transistors here, then this will be voltage divider, and this one cannot be 0. If you have a PMOS, this is completely off, then you can get VDD and ground. But if it's pure NMOS, then you can only get a voltage somewhere in between the VDD and ground. So this is not a full swing of the voltage range. And also you have the static leakage, I think, in this dissipation in this design. So that's not good. So that's why industry abandoned this. And there are some variants of the 4T design, and then you can use those two nodes and to load to be resistor as a node. This is a resistor load. You can use a resistor as the load. Then it's the same problem. Here you don't have the VDD to ground because here is a voltage divider again. And sometimes people use thin film transistor for these two nodes. The thin film transistor is not silicon transistor. It's the transistor at the back end of the LAN. At the interconnect, you have some polysilicon as the transistor. It's not single crystalline substrate transistors. So those are the variants in the old days. But today, the SRAM cell is what we learned before. It's the standard 60 cell, CMOS version. And so this is just some history. But what is more important is this scaling trend, as we discussed before. So if you look at the design rule or technology node from the 130 nanometer down to this 20 nanometer, as we discussed, the physical gate length is LG does not scale too much because of a short channel effect, as we discussed. But the contact poly pitch, or sometimes we call it contact gate pitch, CGP, or if it's poly gate, then CPP. So this contact gate pitch, which is from the contact of your source to the contact of the drain, let's say the center of the contact to the center of the another contact. So this is the dimension that we are scaling actually. So if you look at the scaling here, this CGP or CPP scales well over the technology node. So this is the one that is really scaling. Since the LG is not scaling and CPP is scaling, so what is really scaling is this part, right? If you exclude this LG, think the LG is a constant, then of course LG scale a little bit, but mostly what is scaling is this part. And this part actually has two components. One is the contact size itself, the CT, half CT. Let's say CT is the diameter of this contact, then half CT. And then second one is this spacer. That is the insulator between the gate contact and the drain contact or source contact. You need to fill in here with the dielectric to separate the gate and the source or the gate to the drain. This is your CGS and CGD. So that one is shrinking. That's spacer. So overall, the density is still improving over the generations, and the SRAM cell area actually strictly follows that Moore's law. So like 0.5x per generation in terms of SRAM cell area scaling. So I think this slide is important. So this is the layout for the 60 SRAM cell. And I think one requirement for you, I mean for your homework or for the exam, you are going to read this kind of layout and figure out which is the pull-down transistor and which is the, let's say, pull-up or passgate transistor. If that's a question for you, then how do you do this? Any idea? When you look at this kind of layout, and as a circuit designer, if you use Cadence or whatever software and the CAD tool, then when you view the GDS file, then it's something like this.
Well, the two transistors in the end well, obviously the pull-up. So then midline.
So a few tricks here. Firstly, you want to find, let's say, this box, this is the yellow box here. If it says unwell, even I don't show this label for you. Okay, if I don't show this to you, then you still need to figure out. Okay. so let's say this yellow part, if it says unwell, and you know this is for PMOS region. PMOS is built on top of the unwell. The substrate of PMOS transistor is N-type substrate. So that means this is PMOS region, okay? And then secondly, this one is the gate of the transistor, this green ones. So that means here, this is one transistor. So this is like source or drain. And then this is a gate. So you want to find out the gate first. And then the transistor, you know, the source and the drain are next to the gate. So here, those are two PMOS transistors, basically here, two PMOS transistors. And then those here, there are two transistors here. Right. Those two are NMOS transistors, but the question which is pull up and which is pull down? Any idea? Top one, let's say this one is what?
So you mean which one's a pull down and which one's a pass state?
Oh, sorry, yeah.
Okay.
Yeah. Which one is pull down, which one is pass gate? The top one is what? Pull down. The reason is that here you need to correlate this layout back to the circuit schematic, right? In the circuit schematic, you know, let's draw half of the circuit, right? So this pull down and pull up share the same gate, right? So here, this is the same gate, right? This is the same gate. So this is the PMOS. You already identified this is pull up. Then this one must be pull down, right? And this is pull up. And then, of course, this will be the pass gate. So you should be able to correlate from the circuit schematic to this layout. And here you will notice that the pull down transistor is wider let's say this is a W, this is L, right? This is W and L. You notice that the pull-down transistor is wider than the pass gate. So in this design, you can figure out the ratio pull-down, pass, gate, pull-up is what? By looking at this.
211.
211, yeah, 211. So this is a typical design. And okay, so this is a layout. And then the second question is, what is the cell area in terms of the F square? Right? You have done that homework, and we also discussed that before. So, but if you look at this layout, how do you come up with that number, that 150 F square or 200 F square? So here, let's say in this SRAM cell, let's say the red. You have a question?
Yes. Why is the drain of the pull down and drain of the pull up not connected?
Drain of the pull down. You mean this one?
Yeah.
And the drain of what?
Pull up.
Pull up. You mean this one?
Yeah.
Are not connected.
Needs metal one.
So you need metal one to connect them together. So here only show the contact. I don't think the metal one is shown here. Yeah. So this, and also here you notice that this word line contact, actually the word line is the same for the two pass gates. You need to somehow connect those word line together.
That PD to PG to PO is the ratio of widths, so there is dependence on mobility also of N and P.
This is just this example, right? You can have different ratios. Yeah.